Welcome to lesson 2 from chapter 7, Trigonometry and Modelling from year 2 Pure Maths. And today we're going to look at the double angle formulae, okay, or alternatively known as the double angle identities. Your first job today is to actually derive these double angle identities. Now, I've given you some useful definitions here. It says in the questions which identities to use. So the sine of a plus b here, the cosine of a plus b here, for example, for the first two. And although they're in the formula booklet, I've provided you with them in the useful definitions. Okay, it's the same prerequisites as before. Some year 1 trigonometry will be required. But predominantly we'll be building on what we learnt in the previous lesson in 7.1. So please pause the video and have a go at the 4 questions. See if you can derive the double angle formulae. Okay, and let's have a look at the derivations. Okay, so I've written out the identities that we're going to be using here. We're told to use the sine of a plus b identity here, so that's what I've written down. All right, and we're also told to use a substitution, which I've not got onto yet, but we're going to do that now. So we're going to substitute A for B, or I should say it the other way around, B for A. If you'll notice in the final identity, this is the sine of 2A. We have A's everywhere. So wherever I see a B in this compound angle identity, I need to replace it with A essentially. So that's all we need to do. So let's write out the next step. So therefore, the sine of A plus, and I'm just going to, like I said, replace it with B. With A, like that. So I'm replacing all the B's with A's, is identical to the sine of A multiplied by the cosine of A. And then we add the cosine of A multiplied by the sine of A again, because we're making that substitution across the board. Okay. On the left-hand side of our identity, we can collect like terms inside the parentheses, which is a posh word for brackets. So we have the sine of 2A, just adding those two parts together. A plus A, collecting like terms. Okay, and on the right-hand side, what have we got here? Well, we appear to have the same expression twice. We've got sine A cos A. Now, although they're written in a different order, it doesn't matter. As you'll know, they're the product of the same thing. So we've essentially got 2 sine A cos A's. So we've finished essentially. Just collect them together. So this is just going to be identical to 2 lots of sine A cos A. If you treat the sine A cos A as an object like x. If you have x plus x, you've got 2x. So in this instance, we've got 2 lots of sine A and cos A as a product. So there we go. So we seem to have shown that. Now, moving on to question 2, we use exactly the same process. And if you haven't successfully done this, if you're waiting for me to go through it, maybe just pause the video again and have another go now that you've seen me go through one, because it is the same process. So we are literally going to replace by substitution all the B's across here, and we're just going to see what happens. So let's do that. So your next step is going to be, so therefore you're going to have the cosine again of A plus A. Okay, A plus A, making that substitution for B there. Okay, which is going to be identical to the cosine of A multiplied by, again, the cosine of A, because we're replacing B with A. And then we're going to subtract sine A and then sine of A again. So what happens now? Well, if you notice, again, if we collect like terms on the left-hand side, we're going to have the cosine of 2a. And if you notice now, we have cos a multiplied by itself here, which is, of course, cos squared a. And similarly with sine a multiplied by sine a is sine squared a. So we just have to finish that off. So that's going to be cos squared a. Without even looking at the answer, we know what this is going to be. Cos squared a subtract sine squared a. Now, just as a word of caution here, which is correct, of course, it matches with that. This is where you can get confusion. This is not the same as 1, of course, because cos squared a plus sine squared a would be 1, not the difference. This is a completely different thing. So if you take the difference of cos squared and sine squared, you actually get the cosine of 2a, which is quite interesting. Double the angle, essentially. Now, for questions 3 and 4, we're told to use our answer for question 2, which we've just established. The difference between cos squared and sine squared of some angle is identical to twice the angle. Now, how are we going to show these two variants of the same identity? So it's still cos of 2a here, but now the right-hand side is purely in terms of cosine. Well, if we look at our toolkit, we've now got a new identity, a double angle identity here, and we would really, really like to replace sine squared with something in terms of cos squared. Well, we go back to our toolkit, our year 1 toolkit, and you'll know from experience now, we're going to use this identity. So we're going to use the fact that sine squared a plus cos squared a is identical to 1. And if we want to replace this sine squared a, we're going to have to make sine squared the subject in that identity. So therefore, sine squared a is identical to 1 subtract cos squared a. This is what we're going to substitute into our result from question 2. So let's do it. So cos of 2a is identical to, now going back to the result from question 2, cos squared a subtract sine squared a, which I'm now replacing with this. 1 subtract cos squared a. And notice how careful I'm being with the signs here. Okay, I'm subtracting the sine squared a, so I have to subtract all of this. All right, so I have to put it in brackets. If you don't do that, you'll get the wrong result. So please be very careful. Right, let's see what happens. So if we essentially multiply that bracket by -1, we're going to get cos squared a, subtract 1, and then the double negative is going to give us a positive, which is plus cos squared a. And we can now collect the cos squareds together. So we now have 2 cos squared a, subtract 1, as required. So we have another representation of the cosine double angle identity. Again, if you didn't get that and you've seen this process now, please pause the video, have a go at number 4. If not, just go through the solutions together now. So this time we're going to do the same thing, but we want everything in terms of sine squared now. And you'll see the utility of this later. So we want sine squareds everywhere. We've got our double angle identity from question 2, and we've also got the identity from year 1 that we've been using for a long time now. So this time we're going to use a rearrangement. So I'm just going to rearrange that identity again. The sine squared a plus cos squared a is identical to 1. And we're going to make cos squared a the subject, because that's what we want to eliminate. So if we make cos squared a the subject, that's going to be 1 subtract sine squared a. Okay, and we sub it in. Sub in cos 2a identity. Just in case I've not made it clear. Okay, right, so therefore we're going to have the cosine of 2a is identical to, and we're replacing the cos squared a with this. So that's going to be 1 subtract sine squared a, and then we're going to subtract another sine squared a. I hope you can see that. And let's see what happens now. Well, we've got the 1 again, but now we're going to be taking off 2 lots of sine squared a, which is what we wanted. Okay, so we've now derived 4 identities. We've got 1 identity for sine of 2a or 2 theta or whatever you want it to call it. And we now have 3 variations of the cosine double angle identity. And you're going to see how to use these in the next few examples. Okay, for worked example 1, we have to complete a proof, and it's an identity proof. So we have a rather complicated looking left-hand side, and we have to show that this left-hand side is simply tan theta. Now, I've not prepped this in any way. I'd like to sort of go into this blind so I can show you some possible ways of thinking. So this is something I've not attempted for a while personally. Now, one way to approach proofs like this is just to have maybe do a bit of rough work and see where you want to end up roughly. Now, what I mean is we clearly need to start working on the left-hand side. All right, that's a given, because it's all big and horrible and complicated, and we need to reduce it down to tan theta. It would be very, very difficult to start with tan theta and to arrive at the left-hand side without a lot of manipulation that would not be obvious. So it's a case of simplify all the way down until you get to tan theta. But it's a good idea just to have one eye on some of the preliminary steps. When I say preliminary, I mean the steps that would just arrive before you get to the tan theta. So it's not really a preliminary step. It's some of the final steps. So one of the final steps might be that tan theta is, of course, sine theta over cos theta. You might see that. Okay. So because we're dealing with a left-hand side that already has sine theta and cos theta in it, we're looking to get perhaps a sine theta in the numerator and a cos theta in the denominator. So the question is, how are we going to do it? Well, we also have some other things in our toolkit, don't we? I've used an identity already from year 1, just to kind of preempt what might happen as we embark on this proof. But we also know that we have an identity for sine 2 theta. Now, we've just seen this. You've just derived it yourselves. Okay, it's 2 sine theta cos theta. And I must stress that these are not given to you in the formula booklets. You're only given the compound angle identities. These you're going to have to remember, but as you've seen, which is why I set it for you to do, you can derive them relatively quickly should you need to derive them. But I would strongly recommend that you learn them so that they're at your fingertips. Okay, so I think that kind of forces our hand, doesn't it? So on the left-hand side, I'm going to start off, I'm going to replace the sine 2 theta, which we can see very clearly, and I only have one option, and that is to replace it with 2 sine theta cos theta. So I'm going to do that. So we're going to have 2 sine theta cos theta in the numerator. Okay, and in the denominator, I'm just going to leave it as it is for now. One plus cos 2 theta. Okay, so I've just made my first substitution. Now remember, we want to hopefully create a sine theta in the numerator. So perhaps, I'm not saying for definite, but perhaps we'd want this cos theta to cancel out. I think that would be a good idea. We definitely want that cos theta to not be there somehow. Now let's look at our options. Now this is where we get into the realm of problem solving and where these things can get quite difficult. For the cos of 2 theta in the denominator, we have a choice of 3 possible identities. And this can be a drawback. It's not a luxury, it can be a drawback because you might not know which one to use, which is why I'm kind of sort of planning ahead. So let's just list what our options are. Well, for cos 2 theta, we've got the one we arrived at originally, which was cos squared theta subtract sine squared theta. But we also saw that we could replace the sine squareds with cos squareds and vice versa. So we had another variation, which was 2 cos squared theta subtract 1. And then we also had 1 subtract 2 sine squared theta. Now then, which one do we use? If we choose the top one, okay, we're not really at a disadvantage because we can always just make a substitution and use either of the second or third identities if necessary. But because of what I've just pointed out, because we've got a cos theta in the numerator, and I would like the cos theta to cancel if possible, a good approach would perhaps be to get all of the denominator in terms of cosine. Okay, because if I had sines in my denominator, as in sine sin, that cancellation couldn't happen. I couldn't cancel the cos theta in the numerator, which is kind of what I want to happen. So it looks like my best option would be to select this identity here. Like I said, I haven't planned this. This is just me planning ahead. So I'm going to use that. And if it doesn't work, it doesn't matter. We just go back to the drawing board, or we go back a couple of steps. So this is going to be identical to 2 sine theta cos theta. Kind of forced to write that, so there's not much else we could do. And that's going to be over. Now let's see what happens when I sub it in. I've not mentioned the 1 yet, so I'm hoping that's going to cancel out. So we've got 1 plus. Now I'm going to replace the cos 2 theta with that second identity. So I'll just put it in red. So that's going to be 2 cos squared theta subtract 1. Okay, just using a straight swap from the identity. So the purple bits correspond to each other. Now this looks promising. I've got a 1 and a negative 1. And that's something else you could have been aware of as well. If you want to eliminate the 1, which we don't need, the only way of getting rid of the 1 is to use that second identity. Okay, so it seems to fit both bills. So let's carry on. So we're going to get 2 sine theta cos theta in the numerator all over. The 1s are going to cancel, and we're going to have 2 cos squared theta. Now this is looking really good. We can now see that the 2s are going to cancel. Okay, and we're going to cancel out the cos theta as required, and it's going to cancel with one of these cosines. So I'm just going to be left with 1 cos theta there. So we've got the cancellation there, cancellation there. That's going to be 1. These are going to cancel. We're going to have 1 and 1. So what I'm left with is going to be just sine theta in the numerator and cos theta in the denominator, which is what I anticipated here. We can't see the tan theta directly, okay, but we know tan is sine over cos, so I can now write this as tan theta. So I hope I've given you a few ideas of how to approach these identity problems. They are difficult in the sense that you have choice, and choice can be exacerbating really in problem solving because you don't know which way to go. But again, just reverse engineer it, look at where you want to end up, go back a couple of steps and see if that helps, and then use a process of elimination and see if you can decide what the best identity is to use. So question 2 is, or example 2 is exam content. And in this proof, which we have to do in part A, and then we'll follow up with an equation that we have to make some kind of informed explanation of, we've got a double angle identity, but it's something that we haven't seen before. We have cosec of 2 theta here. So let's just sort of have a little discussion about what this is telling us. Well, cosec, if you'll remember from earlier in chapter 6, if I take cosec of some angle theta, in fact, I won't use theta, I'll use a different letter. Let's use A, which we've been using a lot. Okay, and that third letter rule, always a good idea to convert it into a more familiar reciprocal trig ratio. Okay, so this is going to clearly be from that third letter rule identical to 1 over the sine of A. Okay, whatever A is. So in this situation, I can substitute my A for 2 theta, can't I? All right, so I can just make a note of that. So therefore, the cosec of 2 theta is going to be identical to 1 over the sine of 2 theta. Now, the sine of 2 theta is something we know a little bit about, and we know that we don't have to leave it in terms of 2 theta. So let's start our proof. I think we've got enough to go off now. So let's start with part A. And you'll notice that we're not necessarily starting with the left-hand side every time. So sometimes you're not. So we're going to start with the right-hand side. Okay, so the right-hand side, 2 cosec 2 theta is just going to be the same as 2 multiplying, or 2 over the sine of 2 theta. Okay, from that bit of rough work I did over in the top right. Okay, so that's the first step. So we can eliminate that cosec stuff that we're not as familiar with, and we can bring in the sine function, which we know a bit about. Now that is going to be identical to, so I'm going to keep the 2 where it is. And then once again, my hand is forced now. So I'm forced to write, I've only got one option because everything on the left-hand side is just in terms of theta, whereas the right-hand side is 2 theta. So if I'm going to prove the left-hand side in this proof, I've got to break down my 2 theta into just theta. And the only way to do that is to use the double angle identity, but I think that was pretty obvious anyway. So I'm going to have to use 2 sine theta cos theta. Okay, for that. Now, at the moment, we've got a little bit of cancellation, which is good. The 2's are going to cancel from the top and bottom. Okay, so we've now got 1 over sine theta cos theta. Right, so this is interesting. We could have actually as well gone from this step and just reverse engineered and got to this step here with a little bit of work. So the question is, how are we going to create a tan theta and a cot theta from all this? So that's something we need to ponder. The other issue is, of course, that we have two terms on the left-hand side. We've got tan theta added to cot theta, whereas in our proof so far, we're left with one fraction. So how can we create two terms from this? Well, there is a way to do it, and it's not obvious, which is why I put this in here, because it's a difficult question. Could I write this so it is, instead of having one, I've got two terms, and it also incorporates the sine and the cosine? Well, yes, we can. We're going to use our favorite sine squared theta plus cos squared theta is identical to 1. Now, that's not obvious. Okay, I'll accept that. That is not an obvious step. But once you've had a bit of experience with these things will be something you might consider, okay, as a way forward. So we're going to use that. So I'm going to sub that in. So therefore, we're going to have sine squared theta plus cos squared theta, and that's going to be over sine theta cos theta. Okay, and I realize I've just put a break on the proof there, so that's just jumping down from that step. What can we do now? Well, we can now split this up into two fractions. So I'm going to do that. This is promising. So I've got one thing off my wish list. I'm going to have the two terms at least. They're fractions, but at least I've got two terms. So we're going to have sine squared theta over sine theta cos theta, like that. And we're also going to have cos squared theta over sine theta cos theta. Okay. Now, let's have a look at the cancellation. We've got lots of cancellation going on here. We're going to lose a power of sine in the numerator, and that's going to cancel with the sine in the denominator. The same thing's going to happen with the cosines there. So that's going to be 1, and that's going to be sine theta. And over here, we're going to have cos theta, and that's going to be 1. What happens now? I'll just put the identity in there. So we've now got sine theta over cos theta. Okay, and then we're going to add cos theta over sine theta. Now, you'll remember that cot is 1 over tan, which can also be represented as cos over sine. So we've actually got the result we wanted. So this is cos, this is cot, and this is tan. Okay, and we could have done that again with a bit of rough work. We could have said, okay, perhaps I'm not going to get tan and cot straight away, but perhaps I might get sine theta over cos theta there, and similarly cos theta over sine theta there. So there are possibilities, okay? And I'm going to show you an alternative in a second, which will bring that in again. So it's the wrong way around, but we've got tan theta added to cot theta. Okay, as required. So we've shown that the left-hand side is indeed identical to the right-hand side. Now, you've probably got a bit more space than I have. So let's have a look at an alternative way of doing this. So I'm just going to erase some of my screen. So let's suppose you didn't want to start with the right-hand side this time. You wanted to start with the left-hand side. Well, I've just kind of touched upon what you might want to do. So alternative. So starting with the left-hand side this time, we know that tan theta can be represented as sine over cos. And that cot theta is the reciprocal of tan, which is cos over sine. Like that. Okay. Now, you could say, right, we have two terms on the left-hand side. That's not what I want. I want to condense those down into just a single term. Well, in that case, we're going to need to find a common denominator here and here, which is what we can do. So this is going to be the common denominator. Of course, you're just going to multiply them both together. So we've got sine theta, cos theta. Excuse me. And what's the missing factor on the left? Well, we'd need to multiply this by sine theta here. So that's what we have to do to the numerator. And on the right hand, for the right hand fraction, the missing factor is, of course, cos theta. So you'd have to do the same thing to the numerator. Now, what happens there? Now, this is where it gets interesting. We're going to get sine squared theta plus cos squared theta. A lot more intuitive than the other method, perhaps. When you see that, you can immediately say, well, this is the same as 1, isn't it? So you're going to get 1 over sine theta cos theta. And this is also where that rough work really came in handy before. We want 2 sine theta cos theta to use that double angle identity. Well, we can do that. We just have to manipulate the fraction slightly. So wouldn't it be great if we just multiply the numerator by 2 and the denominator by 2? It means we're allowed to use that double angle identity. So we get 2 over 2 sine theta cos theta. And we're almost there. You'll recognize this as the double angle identity for sine, which is really good. This is identical to sine of 2 theta. And we're at a stage now where we can write down the final answer. So this is, of course, 2 over sine 2 theta, which is what we wanted, which is 2 cosec 2 theta. I mean, what a really nice exploration of trig identities that is. Okay, so there we've now proved that the left-hand side is the same as the right-hand side, which is rather nice. Now, just to finish this question off, it says explain why the equation has no solutions. Well, it's quite a simple answer to this, and you just use the identity that you've just proven. Now, if you didn't successfully prove the identity, don't worry, because you don't have to. The result is given to you. You just have to use it. So I'm just going to create a bit of space here. So the identity that we can now use, whether we proved it successfully or not, it tells us that if you have tan theta plus cot theta is equal to 1, which it states here, then using the identity, we can write down something else. we can actually state, well, if you have tan theta plus cot theta is equal to 1, then that's exactly the same as saying 2 cosec 2 theta is equal to 1. And if we divide both sides by 2, we get cosec 2 theta is equal to 1/2. Now, you'll know from the graph sketching work you've done, cosec is not defined in that interval. Now, the 2 theta, it doesn't matter because it's a transformation in the x direction. It doesn't affect the range of the function whatsoever. So the cosec 2 theta's range is as follows. Okay, it's only defined for values greater than or equal to 1 and for values less than or equal to -1, where 1 and -1 are the only values that it shares with its reciprocal function sine. Okay, once again, the 2 theta doesn't matter. That is a horizontal stretch. Okay, well, it's a scale factor of 1/2. So it just means that cosec is only defined no matter how you manipulate the x direction. The y values, the range, are only defined greater than or equal to 1 or less than or equal to -1. So cosec 2 theta can never equal 1/2. Okay, which means that the equation has no solutions. Hence, tan theta plus cot theta equals 1 has no, and I'm just going to be picky here, no real solutions. All right, and I think stating the range of the cosec function, as I've done here, is sufficient to prove that this equation has no real solutions because it simply can never equal 1/2. Okay. All right, now worked example 3. We have to find another exact value. And we can see here we've got this expression, which we could work out on our calculator directly. But we're not going to do that. We're going to use our brains as opposed to just typing some numbers in on the calculator. You wouldn't receive credit for that, of course. You would have to show a process. So notice it's squared. I've just highlighted the fact that this is squared. So let's expand the bracket. We'll do that first. So if I just write the bracket out twice and we can see what's going to happen here. So we've got sine of 22.5. It's a strange angle to choose. We'll see why in a second. Subtract the cosine of 22.5 degrees. And we're going to multiply this by itself. So we'll just write it out again. So that's sine of 22.5. Subtract the cosine of 22.5 degrees. Okay. So if you see something squared, it's often a good idea to expand and see if you can collect like terms, perhaps, see if there's any cancellation. So at the moment, if I multiply out, we're going to have sine squared of 22.5 degrees. Subtract 2 lots of sine of 22.5 degrees and multiply that by the cosine of 22.5 degrees. Okay, and then we're going to add the cos squared of 22.5 degrees. So I'll just let you sort of digest that for a second. So first up, we multiplied the two sines together. Hence, we got the sine squared here. And similarly, when we multiplied the negative cos by itself, the two negatives cancelled, and well, the two negatives made a positive, and we got the plus. And then we have the collecting like terms in the middle, so we have two lots of the sine 22.5 multiplied by the cos of 22.5. So you've done this before. It's just using awkward looking notation, isn't it? Now, just to remind you, you're probably used to doing this more abstractly, but remember, of course, that if you take the sine squared of any angle theta and add the cos squared of the same angle theta, it's always identical to 1 no matter what the angle is. And it just so happens in this situation, our theta is 22.5 degrees. So this is just as true subbing in 22.5. It's a specific value, isn't it? So in this situation, if I take the sine squared of 22.5, as I'm doing now, degrees, and add the cos squared of 22.5 degrees, now because that's specific, I've subbed in a specific value valid for an identity like that, that's just going to equal 1. So straight away we can see that if I take that term and add that term, it's just going to be 1. Okay, now I've just sort of distorted my working out a little bit. Let's just go down here. In fact, I'll go on this side. So that's going to equal 1 subtract 2 lots of sine of 22.5 degrees multiplied by the cosine of 22.5 degrees. Now, once again, you're going to need to use your Sherlock Holmes detective skills. What can we do with this nasty looking term here? It's got a 2 in the front of it, and it's got both sine and cos of the same angle. So that should ring some bells, shouldn't it? Now, I've alluded to the fact that theta and 22.5, we've got a substitution going on that I've used here. So I've subbed 22.5 in for theta in that identity. Now, if I do the same thing, and I'll just write it underneath so you can see it, this would be the same as 2 lots of sine theta cos theta. Yeah? Now, we know that has an equivalent. This is identical to the sine of 2 theta. That is our double angle identity that we met in this lesson. So I can now just jump to the next step and say, okay, this is now going to be equal to 1 subtract the sine of, now, if it's 2 theta, and my theta is, of course, 22.5, because they have to correspond, I've got to double whatever my theta is. So it's 2 lots of 22.5, because I have to double the angle. Hope that makes sense. Now, if I double that, that's probably where you're wondering, why is it 22.5? Well, you'll see now. If I double that, I get the sine of 45 degrees. Isn't that wonderful? Now, we know a lot about the sine of 45 degrees because we've used it many times before. This is just going to be the same as 1 subtract 1 over root 2. And technically, that's the correct answer. We can actually write that as a single fraction, of course. Now, if I write that as a single fraction, this is going to equal root 2 subtract 1 all over root 2. And you might even want to rationalize that. So if you want to rationalize it, which is a good idea, multiply the numerator and the denominator by the same surd, which is root 2, of course. And this is going to give you 2, multiplying the 2 surds together, subtract root 2 all over 2. So the question is this correct? Have we used our methods of deduction really well? You can check on your calculator. In fact, let's do that. I'm just going to clear some space and we'll just check this on our calculators. Okay, so I'm just making sure my calculator is set to degrees, which it is. Okay, as you can see, just if you need to change your angle unit, please do so, but that's set to degrees. And if we take, open a bracket, we'll just type it in exactly as it says. So we've got the sine of 22.5. Okay, subtract the cosine. So I'm just typing in the question explicitly. Cosine of 22.5, close that, and then we're going to square the entire thing. We get that. Now the question is that 2 subtract root 2 over 2? Let's find out. Try that again. So 2 subtract the square root of 2. Let's come out of that. Try again. Divided by 2. There it is. Okay, so they're the same value. Okay, and our final example, we're going to apply the cast diagram and the right-angled triangle again. This time we're going to do it with double angle identities. Now, I'm just going to stress before I start here. Part B has the double angle 2 theta 4 tan. Now, I'm not going to use an identity for that. But there is a tan double angle identity, but I'm going to leave it for you as an exercise in the following exercise after this lesson to derive that. So I'm going to use the standard approach, which is to say that tan 2 theta is, of course, going to be sine 2 theta over cos 2 theta, which you can write as a tan identity. But we already have results for sine 2 theta and cos 2 theta, so I'm going to stick with those. Okay, so just as a pre-warning before we start. Now what we're going to do is we're going to go straight up to the information given in the question here, and we'll do part A. So we're told that the sine of theta is that, and you can probably guess a common mistake here would be to just double whatever root 3 over 4 is, so root 3 over 2. Now, obviously, that wouldn't be the correct answer, and for those of you who are familiar with the double angle identities, you'll find out why momentarily. Let's get to work then. So for part A, we're told that theta is an obtuse angle. Okay. And we also need to find out some key information. If we're using the sine 2 theta identity, then if I just write down the sine 2 theta identity, just to remind ourselves what we need for that identity, it is, of course, 2 sine theta cos theta, which is relatively simple, and there's no variation on that. Okay, it's the only variant. We've got sine theta already. Okay, that's accounted for in the question. It's a positive value. There it is. So that's fine. We just need to find out what the cosine of theta is going to be. So for that, we're going to need to draw a right angle triangle and use the cast diagram. Okay, so I'll try not to labor this too much because we've done this a few times already. So right angle triangle, and we're going to assume, first of all, that theta is acute. And when we do that, that just means that we can find out the values irrespective of what sign they are. The cast diagram will do the rest. So what do we know? Well, we know that the sine of theta is root 3 over 4, okay, which of course is the opposite over the hypotenuse. So this side and this side we know, so we can just put them in. I mean, they might not necessarily be root 3 and 4. It's just when you compare the two sides, that's what the fraction will simplify to. So we can write root 3 here and 4 there. So the question is, what is the adjacent side going to be? So let's use a bit of Pythagoras. Okay, so the adjacent side is just going to be the square root of 4 squared subtract root 3. I'm just going to be careful here. Root 3 all squared. Like that. And we'll just evaluate this. So this is going to be the square root of 16 subtract 3, which is, of course, the square root of 13. So it's not a triple. It never was going to be because we've got a surd as our opposite side. But we've got a value nonetheless, okay? We can always use Pythagoras' theorem. So the adjacent side should be root 13. Okay, now we've got that, we can now talk about what the cosine of theta would be for an acute angle. So let's write that in. So the cosine, so therefore the cosine of theta is just going to be the adjacent over the hypotenuse, which is going to be root 13 over 4. There we go. Let's not forget, though, that this is for acute theta. So now we need a cast diagram, don't we, just to verify whether this is going to be a positive or negative value when theta is obtuse. So just going up here now. So for theta as an obtuse angle, what's its sign going to be? So just label the cast diagram. Okay, so it's an obtuse angle. Sine is obviously positive for obtuse angles, but we want the cosine. Now, if I put the cosine is obviously going to be negative here. Okay, if theta is an obtuse angle. Okay, only the sine of the angle is positive for obtuse angles. So we can say with certainty, and I know I've labored this a bit, I just can't help it, but maybe over explaining it. So therefore cos theta is going to be, for an obtuse angle, negative root 13 over 4, like so. Great. So now we're in a position to answer part A. So we can now say that for part A, the sine of 2 theta is, of course, going to equal, okay, we're going to sub in some angles, sorry, some values now, 2 lots of sine theta, which is the value that's been given to us. So 2 lots of the root 3 over 4. Okay, and then multiply that by the cosine of theta, which we've just found. Okay, and I should probably make that look important before, so we know that's the one we're going to be using. Okay, not the one in the bottom left, that's for acute theta, remember. All right, so yeah, this is the important one. So multiply by negative root 13 over 4. I mean, if you use the wrong one, you'll just get the wrong sign at the end. Okay, let's put all this together. So that's going to equal, well, it's going to be a negative, isn't it? The 2 will cancel with the 4 on the bottom. So looks like negative root 39, 13 times 3 over 8. Which might not be what you'd expect before this lesson began. Okay, so that's the sine of 2 theta. Now for part B, you might be thinking this is going to be a lot of work as well, but no, we've already done the work. Once we've isolated cos theta and sine theta was given to us, we can now just use the identities. And if you'll remember, we've got we've got sine 2 theta already. That was from part A. So this part here, we've already got. And we also know that the cosine of 2 theta, I can write it in any one of 3 ways. So and just as a precaution, in case I've made a mistake, I'm going to use the sine variant to make sure that I'm using the correct value. Okay, because you never know, I could have made a mistake with the cosine, although it will still give us the wrong answer, but you never know. I just think it's a sensible thing to do. So we know that the cosine of 2 theta will be 1 subtract 2 lots of sine squared theta. So we can use that, no problem, and that's an identity, of course. So for part B, we can just sub in, again, all the values. So the tan of 2 theta is going to be equal to, I'm going to sub in the numbers now, the sine of 2 theta, which we've just found from part A. So I'm going to use this number. Let's plug it in. So that's going to be negative root 39 over 8 divided by, okay, and then I'm going to use 1 subtract 2 lots of sine squared. So that's going to be 1 subtract 2 multiplied by the square of root 3 over 4. So you could just bung all this into your calculator. Square that. Okay, and that will give us the final answer. But with a bit of manipulation, so this is going to be negative root 39 over 8. Let's just tidy up that denominator. And then 1 subtract 2 lots of, now I'm going to square this. So that's going to be 3 over 16. And we're going to have some cancellation here, which is nice. So the 2 is going to cancel. That's going to be 8. So essentially on the bottom, we have got 1 subtract 3 over 8. Okay, so this might actually work out nicely. I'm just going to move down here just so I don't run out of space. So this is going to equal negative root 39 over 8 all over. Now, if I have what I essentially have here for this bit, 1 subtract 3 over 8, then I've essentially got 5 over 8 in the denominator. Okay, I hope that makes sense. And you can multiply here the numerator and the denominator by 8, which will give us a final answer of negative root 39 over 5. So I think that's what you're going to get for tan of 2 theta. And that concludes the lesson.